Hidden in plain sight on the shelves of industrial hardware suppliers right now is a substance costing barely a few dollars, which has been the secret weapon of military contractors, aerospace pioneers, and Formula One racing teams for years. Under rigorous lab testing, it cuts down engine deterioration by an astonishing 90%. It withstands extreme heat that would vaporize standard motor lubricants, and it literally fuses to metallic components at the atomic level, guarding your motor long after the oil pan is bone dry. Yet, if you stroll into a standard car dealership today and quiz the service advisor about it, they will probably stare at you as if you are speaking a foreign language. That substance is molybdenum disulfide, commonly known as MoS2, and the current situation surrounding it within the car business is easily one of the most intriguing and quietly disputed narratives in contemporary mechanics. Because here is the undeniable truth: this is not a recent breakthrough. We aren't talking about some backyard chemistry or pseudoscience. Molybdenum disulfide has been heavily analyzed by NASA and featured in prestigious metallurgical publications dating back to the 1960s. The United States Armed Forces rely on it for their weaponry, aviation fleets, and tactical vehicles. So what is the reason that virtually no one in the everyday consumer automotive space has ever heard of it? That question is going to shadow us throughout this entire discussion, and by the conclusion, you will possess a definitive answer, and you might not appreciate what that answer suggests. Let us begin with what this material actually is, because grasping the underlying science is the key to making sense of everything else. Molybdenum disulfide is a naturally occurring mineral variant of molybdenite, extracted mainly from mines in China, the United States, and Chile. At a microscopic level, it features a unique stacked architecture. Imagine sheets of molybdenum atoms wedged tightly between layers of sulfur atoms. These molecular layers are bound together by incredibly fragile van der Waals forces, meaning they glide over one another with virtually zero resistance. When you introduce MoS2 between two highly pressurized metal surfaces, these molecular sheets shear apart, forming what researchers refer to as a lamellar lubricating film. The friction coefficient of molybdenum disulfide in this altered state can drop to a staggering 0.03. To put that in perspective, the absolute best traditional motor oils typically operate with friction coefficients somewhere between 0.1 and 0.2. That gap is not minor. That is the equivalent of comparing a damp street to a perfectly smooth ice rink. And unlike damp streets, MoS2 does not simply evaporate away. It refuses to oxidize at standard engine temperatures, and it absolutely will not wash off under heavy mechanical load. In a complete vacuum, such as the harsh environment a spacecraft endures, it actually lubricates far more effectively than it does in open air, which is exactly why NASA has integrated it into satellite mechanisms and space telescopes for decades. Now, this is the exact point where things become incredibly relevant from a driver's perspective. Deep inside your vehicle's engine, there are dozens of metallic components, forcefully scraping against one another thousands of times every single minute. Your piston rings drag against the cylinder walls, your camshaft lobes strike the valve lifters, and your crankshaft journal spins tight against its bearings. Every single one of those microscopic meeting points is a generator of metal-on-metal degradation. Every chilly morning start, every hard acceleration to the red line, every split second before the oil pump builds adequate pressure, all of that translates to cumulative, irreversible damage occurring in real time. The vehicle manufacturing industry has been well aware of this fundamental flaw for as long as automobiles have been on the road. Traditionally, the prescribed remedy has always been higher quality oil, advanced synthetic additives, and tighter maintenance schedules. But imagine if a substance existed that could infiltrate those metallic pores, chemically lock onto the surface, and establish an impenetrable armor that remains entirely unaffected by whether your motor oil is brand new, heavily contaminated, or completely missing. That is exactly the function MoS2 serves. Research documented in tribology and surface engineering journals proves that when MoS2 particles enter a lubrication circuit, they don't just aimlessly drift through the fluid like standard commercial additives. Instead, they actively seek out the zones experiencing the most intense friction and heat, the exact locations where severe wear is happening, and they physically plate themselves onto the bare metal. They bridge the microscopic valleys and imperfections, dramatically lower the actual physical contact area between moving parts, and establish a permanent barrier that refuses to wash away into the oil pan. This is an entirely different mechanism compared to a viscosity thickener or a traditional zinc-based friction modifier. Those standard chemicals must remain suspended in the fluid to offer any protection. MoS2 actually leaves a permanent footprint behind. So why isn't this stuff sitting front and center on the display rack of every auto parts store in the country? This is where the narrative gets a bit uneasy. The reason is absolutely not that MOS2 fails to deliver. The academic data leaves no doubt regarding its effectiveness. The reality is much more intricate, and it boils down to identifying who actually profits from mechanical breakdown and who suffers the loss. Consider the economic foundation of the automotive repair and maintenance sector for a second. Petroleum corporations make their money when you require fresh oil on a frequent, recurring basis. Replacement part suppliers make money when your internals grind themselves down and demand swapping out. Service centers rely on scheduled maintenance and major overhauls to keep their doors open. A chemical mixture that demonstrably prolongs the lifespan of a motor, heavily mitigates heat deterioration caused by friction, and allows a vehicle to rack up hundreds of thousands of miles virtually unscathed internally. Well, that is hardly a product those specific businesses are eager to put on a billboard. Now, let me be very clear here. I am not suggesting there is some shadowy cabal of corporate villains in a boardroom actively conspiring to hide MOS2 from you. What I am pointing out is that economic drivers are very real. They dictate where research money flows, what gets heavy advertising budgets, and what your local mechanic ultimately suggests you pour into your crankcase. And the arithmetic is incredibly straightforward. If your power plant survives 50% longer thanks to a cheap additive, that translates directly to 50% fewer crate engines being sold, fewer head gaskets being replaced, and fewer valve train rebuilds being billed. The industries built around selling those items are simply never going to champion molybdenum disulfide in their marketing. There is also a legitimate engineering caveat that historically made some experts hesitate to endorse MOS2. To put it simply, the physical size of the particles matters immensely. MOS2 performs its magic flawlessly only when those particles are exceptionally minuscule. We are talking about dimensions spanning half a micron to 1 micron, or preferably even smaller in the nanoscale range. If the granules are too bulky, rather than bridging microscopic canyons and clinging to the metal, they act essentially like liquid sandpaper and accelerate the damage. This was a genuine concern, and it is exactly why a few early commercial attempts at MOS2 additives earned a terrible reputation. They utilized powders that simply weren't refined enough, leading to highly erratic outcomes. But here is the crucial update to that historical footnote. Contemporary milling and manufacturing techniques have effectively eliminated the sizing issue. Today, you can easily acquire MOS2 suspensions and dry powders boasting guaranteed sub-micron particle grades verified down to the nanometer via laser diffraction analysis. Major players like Liqui Moly, arguably one of Germany's most esteemed lubricant producers, have successfully integrated MOS2 into their catalog for years. Their specific anti-friction MOS2 formula remains one of the top-selling engine treatments across Europe. Fuchs, another massive German industrial oil supplier with an enormous client roster, relies heavily on it for their specialized product tiers. We aren't talking about obscure fringe brands here. These are the exact same corporations formulating factory-fill lubricants for the assembly lines at Porsche, BMW, and Mercedes-Benz. Let us dive into what you will actually notice if you introduce a high-tier MOS2 treatment to your daily driver. Based on testimonials from gearheads and master technicians who have actually run the experiment, and there is a mountain of forum data, teardown videos, and dynamometer sheets to back this up, there are several universal outcomes. Number one, a highly perceptible drop in mechanical clatter, specifically during cold starts, which, as we know, is the most brutal phase of your engine's daily cycle. Number two, a quantifiable decrease in oil temperatures during prolonged high RPM driving, which is a direct byproduct of slashed friction. Number three, and this is the metric that truly catches the attention of mechanical engineers, resurrected compression numbers on heavily worn engines. This happens because the MOS2 has effectively plastered over the microscopic trenches carved into the ring-to-cylinder wall interface. On Reddit communities dedicated to mechanic advice and cars, you can dig through massive threads detailing individuals taking engines well past the 200,000 or even 250,000 mile mark, treating them with MOS2, and watching their compression test results bounce back by 10 to 15 psi across the board. One highly documented case involved a 1998 Toyota Tacoma with roughly 280,000 miles on the factory block. The owner dumped an MOS2 suspension in with a routine oil change, drove another 30,000 miles, and then actually pulled the cylinder head to inspect the bore. The cylinder walls, which he heavily photographed and uploaded, clearly displayed a distinct dark gray sheen precisely in the friction zones. The MOS2 barrier was still there, completely unbroken, having successfully endured multiple standard oil drains in the interim. Now here's a massive detail that almost everyone arguing about MOS2 on the internet completely overlooks, and it fundamentally alters the entire value proposition. The most catastrophic damage your engine ever endures doesn't happen while you are cruising down the highway. It takes place within the initial 10 to 30 seconds of a cold start, well before the oil pump can push fluid up to the critical components. Research from the Society of Automotive Engineers suggests that these cold starts are responsible for roughly 60 to 80% of the total mechanical degradation an engine suffers in its lifetime. Let that sink in. Most of your engine's death by 1,000 cuts happens while you are just sitting there waiting for it to warm up. Because molybdenum disulfide physically clings to the metal as a permanent shield, it is already on duty during those agonizing, oil-starved seconds. Standard oil additives are completely useless here because they are sitting at the bottom of the oil pan. By the time your conventional synthetic has finally reached the top end, MOS2 has already been defending your engine for 15 seconds. Over the course of 3,000 cold starts, a completely average number for a decade-old car, that protective head start prevents a staggering amount of metal loss. The actual application process is another detail we need to cover, mostly because it shocks people how simple it is. You don't need a mechanic's toolset to use MOS2. The most consumer-friendly version is a pre-mixed liquid suspension, basically the microscopic particles floating in a carrier fluid that you just pour straight into your oil fill tube. A typical passenger car takes about 1 to 200 milliliters, ideally added alongside a fresh oil change so it cycles through perfectly. Some purists opt to buy the raw powder, mix it with a bit of oil themselves, and pour it in. And the price? A treatment that will guard your engine for an entire oil change interval through thousands of heat cycles will set you back somewhere between $2 for the bulk powder up to maybe $10 for a premium pre-bottled suspension from a company like Liqui-Moly. Think about that for a second. A single quart of high-end synthetic oil costs more. A single spark plug costs more. You can't even buy a dealership oil filter for $10. From a purely financial standpoint, especially if you are nursing an older engine that is already showing its age, the argument to at least try this stuff is basically bulletproof. There is one final layer to this narrative that we have to discuss, and it involves the current electric vehicle revolution. Because while everyone talks about MOS2 saving gas-guzzling internal combustion blocks, it has massive implications for EV platforms as well. Electric drivetrains face their own intense friction and heat hurdles, specifically inside the reduction gearboxes, the high-speed motor bearings, and the thermal paste used to cool massive battery arrays. Engineers at MIT, alongside top research teams in Germany and Japan, are aggressively developing MOS2-based dry lubricants specifically for electric vehicle motors. It is also the go-to solid lubricant for aerospace actuators, robotic limbs, and micro-manufacturing gear. The point is, this isn't some obsolete grease that will vanish as we transition to battery power. It is an actively expanding technology because it relies on the unbreakable physics of a crystal structure rather than a chemical reaction that eventually sours and breaks down. So what is the takeaway here? If your daily driver has crossed the 50,000-mile mark, and especially if you are noticing a bit more valve train ticking, a dip in your gas mileage, or you're having to top off the oil between changes, all classic symptoms of internal wear, a high-quality MOS2 treatment is arguably the cheapest insurance policy you can buy. The chemistry is undeniable. The real-world industrial track record is flawless. And at $10 a bottle, the barrier to entry is basically zero. The reason it isn't common knowledge isn't a lack of performance. It's simply because the massive infrastructure that dictates how we maintain our cars is built to sell you replacement parts and frequent service appointments, not lifetime engine protection. MOS2 threatens that cycle, so it remains hidden in plain sight, quietly utilized by the engineers who actually understand material science. Well, now you are one of those people. What you do with that knowledge is entirely up to you. If you found this deep dive helpful and want to uncover more of the hidden engineering that shapes our world, hit that subscribe button, leave a comment below, and I will see you in the next video.